Okay, and let's continue with operational amplifiers. So this is pretty much basic component of any electronic device nowadays. You see a classical type of operational amplifier here, but there are many other types. And this is an interesting device. It's an active component, meaning that we are mostly looking at the inputs and outputs, but it is supplied by minimum and maximum voltage. And one thing which makes this very useful and very interesting is that the gain of the amplifier is extremely high. So it reacts very well on the difference between input legs. So and then without the feedback control, it goes either V max or V minus voltage if you have even slightest difference in the inputs. But once you apply feedback to operational amplifier and you apply it on the negative leg, so then you get a reasonable amplifier which has very good characteristics. So input impedance is very high, so it doesn't draw current in itself. Okay, it's supplied by other current, but when we are doing the signal analysis, we assume no current flows in the amplifier. We also assume that the gain is high, and operational amplifier is linear in terms of gain. So you can visit, let's say again, Wikipedia or electronic books and study more. You will soon see how they are applied in the context of filters, integrators, derivators, in context of control. So if we now apply our rules and we make this type of setup where we have a negative feedback by resistor 2 and input resistor 1 before our operational amplifier, we can analyze what type of behavior we have, and we can analyze what is the closed loop gain, bearing in the mind that no current flows in the legs and the voltage between the legs is always the same. That comes from the assumption that your gain is very high, so it always keeps the voltage the same. And we can use this potential now, saying that if we have 0 volt here, we have also 0 volt here, and then all the current has to flow in this way. So and that makes our analysis quite easy. We can calculate the current which is derived from the equation. So input voltage has to be this voltage minus resistance 1 times the current. And now this voltage happens to be 0 because the V plus is zeroed. So output voltage is yield similarly. So it's this voltage which is 0 plus resistance 2 times the current. And now we can get something like closed loop gain. So amplifier's output divided by input is minus R2 per R1. And this we can use further. We can generalize it in the context of impedances as well. But let's look at another. If this was inverting amplifier, now we have non-inverting amplifier. So we can again derive transfer function. Now our input goes here, and this leg immediately follows the input if we keep the same rule that the voltage must be here the same. And now this point is grounded. So whatever voltage you have here, you can always calculate the current what is flowing here to 0 volt because you know that this is at some potential and this is at 0. So you can calculate the current here, and then you can say that the same current is actually flowing from here because this leg is neither drawing or outputting any current. So then you can calculate the output voltage by adding input voltage, which is the same here, and solving the current from here. And now you get the closed loop gain output over the input, which is sum of resistors divided by resistance 1. So now we have learned two amplifier setups, inverting and non-inverting. And now we can study how to use them in the context of filters and transfer functions. And then we go further to body diagram and analyze the frequency behavior. So this inverting configuration we can generalize for the impedances. Now this Z1 and Z2, it can be anything from resistance, capacitance, inductance. And now we actually achieve a table. So if we put resistor in both impedances, we get amplifier. If we want to get derivative, we can put the capacitance in Z1, or if we want to get integrator, we put inductance in Z1. And this is later used in the exercise. You are given a transfer function which you should achieve by using these tables. So now we can look at the low pass and high pass filters, which you have studied already in preliminary exam. So we can do low pass in this way and high pass in this way. How do you see that the other is low pass and the other is high pass? So if you remember that capacitance was pretty much open circuit for DC voltage and pretty much shortcut for high frequencies because the denominator goes large here. So you can already see that nothing is happening here if your frequency is low, but once your frequency approaches infinity, this capacitor becomes a shortcut, and then your input is here in this leg and this leg is the same, so your input pretty much follows the output. And over here you can see that if you have a DC current, it tries to go here. Okay, it cannot go here. It doesn't go here either because capacitance is pretty much open circuit. Nothing happens. But then if you have a high frequency, this becomes more like a shortcut, and then this leg and this leg, again they are in the same potential, and it follows. So you can also kind of like by reasoning recognize which is high pass and which is low pass filter. So this analysis of transfer functions by body diagrams, it is somewhat outdated or old-fashioned, I must say. Pretty much you do everything in MATLAB or similar tools nowadays, but I try to carry you through body diagrams in order to give some insight about high pass and low pass filters and frequency behavior of transfer functions. Pretty much if you draw something manually nowadays, you quite quickly you check it with MATLAB that everything went okay, and numerical methods are overruling or dominating over manual methods. But still it would be good to have some type of insight how different systems behave at low frequencies and high frequencies. So this I pretty much leave you to study how to make manual body plot. I just say quickly that we have usually rather low order polynomials. Numerators are often first or second order, and denominators are also like first or second order. And always if you have like a numerator, let's say first order, 1, 0, meaning first order polynomial, increases the gain 20 decibel per decade, and denominator vice versa decreases the gain. If you have second order, it is 40 decibels. But we'll do this more profoundly in exercise, and you can always revisit these rules. Corner frequencies we try to recognize, so where is -3 dB frequency? That is important for filters, for instance. So, and what we have been doing in lecture quizzes, we have analyzed body plots in such a way that we have looked what is the DC gain, so we have put frequency at 0, and then we have increased frequency to infinity and studied the polynomial, what is the limit value it will approach when omega approaches infinity. Now we have like a start point and end point for our analysis. Then we try to analyze what is happening in between. Do we have zeros, meaning that your response goes to 0? Do we have poles or resonances, meaning that your response goes very high? So let's take simple low pass filter here. So this is our gain, and this is our phase, and our transfer function is there, k over s plus a. So our corner frequency here is a, so meaning that something will happen at corner frequency. And now in logarithmic scales, that's what will happen is that the gain start to decrease, and the rate of decrease is now dependent on the order of the polynomial, which is 1 in this case. So it will decrease -20 dB per decade, and it will stay constant from 0 to that corner frequency. Now if you draw it with MATLAB, for instance, you see that this is not really like sharp. It has round edges, and you will get more accurate answer. But this is basically, you know that this is basically your amplitude behavior. And then your phase behavior is such that the phase starts to change already 0.1 times corner frequency, and it will change until 10 times corner frequency. So it's much smoother. And how much it will change? Now it's again the order of polynomial. Each pole will decrease gain by 90 degrees. So it will start from 0, so meaning that input and output are in phase. Closing to corner frequency or resonance means that output starts to lag versus input. And then in high frequencies it will be lagging 90 degrees in this case. So then let's say you want to make a bandpass filter, for instance. So then you have to make actually numerator some larger order than zeroth order. In this case you have made first order numerator and second order denominator. And this means that your gain will be increasing. It will be 0 at 0 Hz, so nothing goes through. And then it will be increasing 20 dB per decade until it reaches corner frequency, omega naught. And now this is second order, so it will start decreasing 40 dB per decade. But as it was increasing 120 dB is consumed to make the curve flat, and another 20 will turn it down. So now you get this type of bandpass behavior where the highest gain is at omega naught. And again, in the phase, the changes start 0.1 times omega naught and end 10 times omega naught. And since you had this bandpass behavior or high pass behavior here, it's like a derivative. You are starting from 90 degrees and then you are going down by 2 times 90 degrees, meaning that you end up at 90 degrees. Quite confusing, isn't it? But if you take MATLAB and you start to design filters, I think it will become more clear for you. And also, like exercise, we revisit these and use numerical methods to analyze. So these are a bit of extras, so I wanted to draw this because this is very much how resonating systems are looking like. So if you have like a mass spring damper system, you will get this type of behavior where your amplitude is relatively flat, and then you start decreasing 40 dB per decade after this frequency B, which is resonance, and the phase goes from 0 to minus 90 degrees. Sorry, minus 180 degrees. And this is even complicated, more complicated. Now you have like a DC gain, and then you have a 0 which starts to increase the gain at frequency C, and then you have a resonance which starts to decrease the gain at B. And the phase goes from 0 to plus 90, and then it goes back to 0 and minus 90. So you can always calculate the phase change directly. First order here means plus 90, and second order here means plus 180. So 90 minus 180 equals 90 degrees. So as a conclusion, use MATLAB. Even I tried to explain it on the pen and paper. And you have quite many tools there. You can check Bode plot, freak response, Nichols, Nyquist, spectrum functions, for instance. And this manual analysis is only to get insight in the system, not so much to get accurate answers. Now you could actually stop and think where you can find such dynamic systems. I would say that you find them pretty much everywhere. My quick tip is that, for instance, resonators are required for accurate timing, maybe large amplification, coupling or decoupling systems, etc. You will use little bit decibels also in the exercises, and I have been using decibels in the lecture. So this is pretty much background material, and you have already calculated decibels in basic maths. But this is just to remind you that it's a logarithmic unit where you can express a ratio of two values. And historically it has been easy to express large numbers, and also make easier to calculate because multiplication becomes summation and power becomes multiplication. So it has been handy way. Again, I think numerical methods are pretty much overruling this, but still engineer needs decibels, and engineer needs to understand what means if you have decibel scale. So couple of exercises. So how if your signal amplitude decreases from 1 to 0.5, how many decibels is signal attenuated? How much power has been reduced? You can think about these answers. I think you can see these here, and then you can also like calculate or think about this type of situation where you have different gains, and now in this case they are rather easy to multiply, but if the numbers were big they were not so easy to multiply. But if you knew the gain of each stage by decibels, it would be easier to sum them up. But yeah, more about this in exercises. Okay, group work and lecture quiz. I remind that lecture quizzes are now multiple choice in my courses if you are participating in this course. If you are watching this for fun, you can do this on the pen and paper. Hopefully someone does this for fun as well. So draw manually body plot, gain and phase of transfer function x over fs, and your differential equation is here. And now I have already actually tipped you that this is a mechanical resonator, and the transfer function is 1 over ms squared plus cs plus k. If you substitute s by j omega, you can analyze that at low frequencies the response is 1 over k, and for high frequencies it's pretty much 1 over m. So you know start and end points. Now you have to decide where your resonance is, and if you remember, finding a way to find the resonance was that you divide the equation in such a way that you have a coefficient 1 here in the highest order of derivative or highest order of Laplace, and then you have a resonance here, or actually you have a resonance squared here. So the resonance is square root k over m. And now with the given Bode rules, you can start from 1 over k and end up to somewhere to low figure proportional 1 over m, or high frequencies, and put the kneeling point at the resonance. So then we are asked to design an integrator circuit by using the 2 op-amp circuits in series, and we are required to have the transfer function 1 over s. And then we are asked to draw schematics and select the component sizes. So how would you do this? I recommend you to revisit the table I had earlier. over here and look at this table. So basically our closed loop gain is minus Z2 per C1. And now we require this to be 1 over S. How would you do it? So you can select, for instance, this setup here. But then you have a problem with this minus sign. What do you do? How do you get rid of the minus sign? So you can use two minus signs to make it positive. So you can, let's say, select one setup here, giving this 1 over S behavior, and then having another setup with resistances only and getting rid of the minus sign. Then you will have 4 values to decide. You have resistance 1, capacitance for the first setup, and then you have resistance 1 and resistance 2 for the second setup. And now you have to work out these values in such a way that the whole transfer function will be 1 over S. So typical, let's say if you select this type of setup, typical capacitor values are order of picofarads or less than microfarads maybe, and typical resistance values are tens of kilo ohms. So those values might be kind of like realistic, but basically you will see the idea even you use, let's say, 1 ohm resistors, but you will end up very high capacitance values, and those capacitors may not be easily available in practice, but you will get the idea at least. And now it doesn't matter whether the first one is with the capacitor or the first one is with the resistance, because we are assuming these circuits are linear. You can always interchange. You can have like resistance circuit first or resistance circuit second. Let's go to the final question. So explain the circuit 74F148, which is used to AD conversion. What it takes as input, what it takes as output, and what is the purpose of the circuit. So I pretty much already explained the circuitry there. And if you want to have more insight or better explanation, you can Google this and you find a lot of material. Again, thank you for watching and good luck. See you later.